Hello, and welcome to another homework solutions video. In this video, we're going through some of the problems in the Chapter 7 problem set. I've posted timestamps in the description of this video, so you can jump ahead to whichever problem you'd like help with, or if you just want to work with me through all of these, you can do that as well. All right, so let's start here in section 7.1, question number 4. So we're given that a, b, and c are integers with a not equal to 0, and what we want to prove is this. If a divides b and a divides b plus c, then a divides c. All right, so proofs in this section are going to most of them just come down to rewriting what things mean. What does this mean? What does this mean? And what does this mean? So let's just start there before we start trying to prove this. A divides b. What is the definition of a divides b? What do I know if I know that a divides b? I know that b equals a times some integer. Let's call it x. What do I know if a divides b plus c? Well, that means I can write b plus c as a times some other integer. Let's call this one y. And my goal, so I'm assuming those things. My goal, what would it look like to prove that a divides c? What do I need to show in order to show this statement? Well, I need to write c as a times some other integer. Let's call it z for now. So that's our goal here, is to come up with this integer so that c equals a times that integer. And we're going to use these two things. All right, so let's prove this. Proof. So let a divide b and a divide b plus c. Then we'll use the definitions. Then b equals ax and b plus c equals ay for some x and y. Just like when we did evens and odds, remember to use a different variable, right? We can't say that this is a times x again. That would imply that b plus c is equal to b, which would mean that, right, c is 0, and that's not one of our assumptions that c is 0. Okay, so we have these two bits of information, and we'd like to combine these in some way to arrive at an equation where c is on the left-hand side, written as a times something else. So I have a way to do this in mind by subtracting the two equations. So if I take this equation and subtract this equation, that'll leave me with just c on the left-hand side. And then both things on the right-hand side will be multiples of a. I can factor an a out and figure out my z. But I'm actually going to show you something. I was in office hours working with another student who had their own idea of how to do this, so we're going to use that. So I'm going to use the fact that b equals ax, and, well, I see a b over here in this equation, so I'm going to substitute that in. So that means that ax plus c equals ay. And again, if we keep in mind what we're looking for, an equation with c on the left-hand side, I can see, all right, let's solve for c here. So then c equals ay minus ax. Do I have this equation yet? Not quite. Let's factor an a out, a times y minus x. And since y minus x, since y is an integer and x is an integer, y minus x is an integer. So what's our conclusion? A must divide c. We wrote c as a times some other integer, so a divides c. How cool is that? Done. All right, let's move on. Let's see. So here we're given that a and b are integers and that 3 divides a. So right off the bat, I know that a equals 3 times, I don't know, I'm going to call it k this time, 3 times k for some k. And I want to prove this implication. If 3 does not divide a plus b, then 3 does not divide b. So whenever I see an implication like this involving not divides, I know what divides mean. I know how to write down, right? If I know 3 divides a plus b, I know how to write that down, right? I know a plus b equals 3 times some k. But not divides, well, that introduces some other possibilities into it. If we can avoid that, we should do that. So how can I avoid that? How can I turn these negative statements into positive statements? Well, I can prove the contrapositive. So instead of proving the statement directly, I'm going to prove the contrapositive. That is, if 3 divides b, then 3 divides a plus b. So I'll prove that instead, because that's more positive, and I'm a positive kind of thinker. Right? Power of positivity. Okay. So we know this. This is part of our assumptions, and then we're going to assume 3 divides b. So assume, let me write proof. We are proving this thing. Proof, assume 3 divides b. Then b equals, I don't know, let's say 3l for some integer l. And then we have, okay, so we have we have a equals 3k, and we have b equals 3l. So how about a plus b, right? If 3 divides a plus b, I need to get there, so I need to write a plus b equals 3 times some other integer. Well, I have an expression for a, and I have an expression for b, so let's add those together. So this would be 3k plus 3l. And, well, that's 3 times k plus l. So that is 3 divides a plus b, because k plus l is an integer. And that's what we wanted to show, that 3 divides a plus b. All right, we got it, done. We're just following our noses, writing down what our assumptions are, noticing when to use a contrapositive. If our original statement is an implication with 2 negatives like that, a contrapositive seems likely to work. And then just writing down what each statement means, and then doing some kind of combination to get them together. So those are those first 2, but what about number 12? Here we're asked to show that if 3 divides, or that just for all non-negative integers n, that 3 divides 2 to the 2n minus 1. So hopefully you identified by looking at some examples in the book that we should try induction on this one. And in general, that's, a pretty good idea when we want to show something for all non-negative integers. So our base case, so let's say proof, and I'm going to say here by induction. And so I'll start with my base case. Well, if n, our base case here would be n equals 0, right? Because that's the smallest, that's the least element in this set that we're considering. So if n equals 0, then what? 2 to the 2n minus 1. Well, that's 2 to the 0 minus 1. 2 to the 0 is 1. So I get 0. And does 3 divide 0? Yes. Everything divides 0, except for itself. And 3 divides 0. Cool. So that's a base. So we have a base. All right, so assume induction hypothesis. Let's assume that 3 divides 2 to the 2k minus 1 for some k greater than or equal to 0. We can just use weak induction here. We don't need to use strong induction on this one. And what do we want to show? I'll write this in red because it's not really part of the proof. Want to show that 3 divides 2 to the 2k plus 2 minus 1. Why 2k plus 2? Because the next case would be when k is k plus 1, and 2 times k plus 1 is 2k plus 2. So that's the next case we want to show. Okay, so what does this tell us? Let's look over here at our assumption. What does this tell us? This tells us that 2 to the 2k minus 1 must be 3x, let's say, for some x. And I'm actually going to solve for 2 to the 2k here. 2 to the 2k equals 3x plus 1. We'll see why in a second, why I might want to solve for 2 to the 2k there. Now, so what do I want to show over here? Well, this is true if and only if I can write 2 to the 2k plus 2 minus 1 equals 3 times some integer over here. So I'd like to look at this expression and hopefully use my induction hypothesis, use this fact, to write this thing as 3 times something else. So that's the strategy. So let's go ahead and write that thing out and see if we can manipulate it. 2 to the 2k plus 2 minus 1. Well, all right, how else can I write this? How can I, and really I'm looking for a way to involve my induction hypothesis, the fact that 2 to the 2k is 3x plus 1. So how can I just get 2 to the 2k? Well, I want to get rid of this plus 2 here. I don't like that plus 2. That's mucking everything up. But remember that, right, if I have like 2 to the a times 2 to the b is 2 to the a plus b. So I'm going to factor out that plus 2. So this is the same thing as 2 squared times 2 to the 2k minus 1. 2 squared is 4. So this is 4 times 2 to the 2k minus 1. And look, so if you didn't solve for 2 to the 2k yet, now it should be clear that you should. And why we would want to is, well, we have 2 to the 2k right here, and I have an expression here that involves 2 to the 2k. So we solve for 2 to the 2k. We see it's 3 times some integer plus 1. So let's go ahead and write that down. By the induction hypothesis, this is 4 times 3x plus 1 minus 1. And now we have some simplifications we can do. So this is what, 12x plus 4 minus 1. That's 12x plus 3. Ooh, I can factor 3 out now. This is 3 times 4x plus 1. And so that implies then that 3 divides 2 to the 2k plus 2 minus 1. Because I have this guy, 2 to the 2k plus 2 minus 1, written as 3 times some integer. And I know this is an integer because x is an integer. That's the proof. By induction, it holds for all n. Beautiful. All right, let's move along. Whoop. Got to catch myself there. Moving on to section 2. Every prime except for 1, not the number 1, but except just 1 prime, can be written as a squared minus b squared. So, there was a really nice post in the discussions about this one. Someone put a nice path to a solution for this one, describe what they did, and I liked what they had said, so I'm going to try and describe it like that. So first thing to notice here, before I even start writing a proof, is I'm just going to look at what does it mean for a squared minus b squared to be prime. So I'm just going to assume a squared minus b squared is prime. I'm not proving this statement yet. I want to see what a squared minus b squared being prime implies. So I'm going to assume that, well, a squared minus b squared, well, I can write that as a minus b times a plus b. In particular, since I have it written as the product of these two things, well, a minus b must divide a squared minus b squared then. Same with a plus b has to divide a squared minus b squared. But a squared minus b squared is prime, right? So the only things that can divide it are 1 and itself. And so that means one of these things is 1, and one of these things is a squared minus b squared, the original thing. So which one is 1 and which one is a squared minus b squared? Well, a minus b must be 1 because it's smaller than a plus b. So what that would tell us then, so if a squared minus b squared is prime, that means a minus b must be equal to 1, which would tell us that a is 1 more than b. So if this is prime, then a and b must look like this. And so that actually tells me quite a bit. And what would a plus be in this case? A plus b must be, add b to this equation on both sides, 2b plus 1. And I know that a plus b is equal to a squared minus b squared. So this is kind of giving me the general form, is that it's going to look like an odd number, that a squared minus b squared, right, this is the same thing as a squared minus b squared, is looking like an odd number. Well, what do I know about primes? I know they're odd. So I'm going to start proving this now. Proof. let p be a prime. And I'm actually going to let it be an odd prime. So what I'm doing here is I'm claiming that the 1 here is 2, when p is 2. I won't be able to do it because what I showed down here was that if I can write a squared minus b squared as a prime, then we must have that a squared minus b squared is odd. So that doesn't tell me that every odd prime can be written like this. It just tells me that if an odd prime is written like this, then it must be odd. And so hence we get rid of the case when p is 2. So let p be an odd prime, so that's p is greater than or equal to 2. Then, well, since it's odd, I can write p equals 2k plus 1 for some k in the integers. And in fact, non-negative integers, we could say positive integers, something like that. That's fine. And then p equals 2k plus 1. And then, so in order for me to prove this, I need to show that I can write p as a squared minus b squared, which I know looks like a minus b times a plus b. And I know the relationship between a and b because of this. So I'm going to decompose this 2k plus 1 into a plus b. So notice that this is the same thing as k plus 1. So I'm going to let a equal k and b equal k plus 1. Then, oh, sorry, I want to do it the other way. Let a equal k plus 1 and b equal k. Yeah, I'll do it like that so it matches what we did before. Then what? A squared minus b squared is k plus 1 squared minus k squared. K plus 1 squared is k squared plus 2k plus 1 minus k squared, which is 2k plus 1, which is my prime, p. And so I have a squared minus b squared with this a and b equal to my prime. Proved. Oops. Uh-oh, something happened. Technical issue. My WebEx went off because I was away from it. All right, so that's proved. We've taken an arbitrary odd prime, which is every prime except for 2, and we wrote it as a squared minus b squared. Pretty neat. Let's move along. Question 10, only one prime has the form n cubed minus 1. So it's almost like the kind of an opposite of the last problem. Last one, every prime except for 1 had that form. This one, only one prime has this form. So we're gonna try and investigate this the same way. I'm going to assume that n cubed minus 1 is prime and just see what consequences of that are there. So assume n cubed minus 1 is prime. What happens? Well, notice that I can write n cubed minus 1. Now, this one might be tricky because maybe you don't remember or you've never learned a difference of cubes formula, but nevertheless, there is one. N cubed minus 1 is the same thing as, oh boy, I have to remember it for a second. N minus 1 times n squared plus n plus 1. So we can go ahead and compute that and double check ourselves. N squared, n1, and minus 1. I'm going to do area model for multiplication because it's how I like to multiply things. N squared, n minus n squared, minus n minus 1. N squareds cancel off, minus n and n cancel off. I just get n cubed minus 1, which is what was claimed. So that actually works. That's how you can factor a difference of cubes. And now notice what I have here in terms of divisibility. So I'm assuming n cubed minus 1 is prime, but now this is telling me that n minus 1 in particular has to divide n cubed minus 1. We also know that n squared plus n plus 1 has to divide n cubed minus 1. But let's just focus on the n minus 1 has to divide n cubed minus 1. So again, I know that since n cubed minus 1 is prime, that n minus 1 is either 1 or it's n cubed minus 1. So there's two options there, so that's going to split this into cases. So case 1, n minus 1 equals 1. And then the other case, maybe let me write the other case first before we start chasing these down. Case 2 would be that n minus 1 is actually equal to n cubed minus 1. And that's going to turn out to be bogus. But case 1, n minus 1 equals 1. Well, what does that make n? Then n is 2. And then n cubed minus 1 would be 7. So that works. 7 is prime. So the only prime right now that we found that works would be when n is 7. Only one prime? Well, that's n equals 7. Or sorry, n equals 2. Which implies that n cubed minus 1 is 7. So it looks like that's going to be the only prime that we can write this way. Because if it is prime, then n minus 1 divides it. And if we're in this case, that means n is 7. Or then n cubed minus 1 is 7. Case 2, well, what if n minus 1 was really the same thing as n cubed minus 1? Well, let's solve this equation. I'm going to subtract n and add 1. I get 0 equal to n cubed minus n. N cubed minus n I can factor, n squared minus 1. I can factor that yet again. This is n times n minus 1 times n plus 1, which tells me that n is either 0 or n is 1 or n is negative 1. And let's figure out what n cubed minus 1 is in each of these cases. In this case, n cubed minus 1 would be negative 1, which is not prime. When n is 1, n cubed minus 1 is 0. And when n is negative 1, I get negative 2. So if n minus 1 was n cubed minus 1, then n cubed minus 1 would be negative 1, 0, or 2, none of which are prime. And so this whole case can't happen because we're assuming n cubed minus 1 is prime. Okay, so if this thing is prime, then since case 2 can't happen, case 1 must happen. And if case 1 happens, then n cubed minus 1 is 7. Hence, there's only one prime that can be written in this form. That's the proof. Pretty cool, right? I like that one. I think that one's pretty sweet. Try and run through that logic a little bit later after you've watched this video. See if you can still recall it and go through that argument. And you might find a different argument here as well. Okay. Oh, I kind of ran over on this problem. Oops. If 3 does not divide n, then 3 divides 2n squared minus 5. All right, so one of these divisions is negative, right? I say 3 does not divide n, and then 3 does divide 2n squared minus 5. So even if I do a contrapositive, I'm going to end up with a not divisible statement, which I don't like. So I'd like to take, of the two not divisible statements there can be, this is sort of the simpler one, and so I'd like this to be my assumption. So I'm going to do this one directly. So what does it mean for 3 to not divide n? Well, that means that n mod 3 can't be 0. And so that means n mod 3 is either 1 or 2. So let's start there. Proof. So we'll assume 3 does not divide n. Then n mod 3 equals can't equal 0. Otherwise 3 would divide n, right? So then n mod 3 is equal to 1, or n mod 3 is equal to 2. So those are our two cases, right? Whenever we divide something by 3, we'll either have a remainder of 0, 1, or 2, and we know 0 can't happen. And so now we'd like to show that 3 does divide 2n squared minus 5. So I'd like to, again, now write out what these things mean. So since this is split up into two, an or statement here, if 3 does not divide n, then we have these two possibilities. This is what's telling me, hey, we should use cases here, that there's two possible cases that could happen. So case 1 is going to be when n mod 3 equals 1. Case 2 will be when n mod 3 equals 2. So what does it mean for n mod 3 to equal 1? Well, that means I can write n as a multiple of 3 with a remainder of 1. So that means n equals 3k plus 1 for some integer k. Okay, and then I'd like to make some statement about 2n squared minus 5, so let's compute that. So then 2n squared minus 5 is, okay, that's 2 times 3k plus 1 squared minus 5, 3k plus, so that's 2 times 9k squared plus 6k plus 1 minus 5. And what do we get now? That's 18k squared plus 12k plus 2 minus 5. So 18k squared plus 12k minus 3. Well, 3 goes into 18, 12, and 3, so I'm going to factor a 3 out of this. So this is 3 times 6k squared plus 4k minus 1, which is an integer. Hence, 3 divides 2n squared minus 5. Cool, case 1 is done. We showed that 3 divides 2n squared minus 5 in that case. Case 2, all right, well, what does this mean for n mod 3 to equal 2? That means I can write n as 3k plus 2 for some integer k. Notice here I can use k again because this is a totally separate case. I'm done with my argument in case 1. This is now a new world, a new universe where n is equal to 3k plus 2. In different cases, you can use the same variable across cases. It's fine. Sort of starting fresh. And then you can do the same thing. So I'm actually going to end this one here. I'm not going to completely finish this. I'm going to let you try to finish it. So now what would the next step be? Well, do 2n squared minus 5, see what you get. Hopefully it's a multiple of 3. It will be. And then you'll be able to conclude 3 divides 2n squared minus 5 in that case, and that'll prove the statement completely. So I'll let you finish that one. Let's move on to the next problem. All right, number 20 in section 3. That was, by the way, 7.3, number 14. 7.3, number 20. For all primes p equals 4k plus 1 or 4k plus 3. All right. So this one might have been a challenge, and I think when you see the proof for this, you're going to, groan. There's going to be an audible groan there. So for any integer, if I divide it by 4, if I use the division algorithm on n, I know that there's only, 4 possibilities that could happen. Then n equals 4k, n equals 4k plus 1, n equals 4k plus 2, or n equals 4k plus 3. This is what it means. There's another problem that asks this. What does it mean to describe what happens when you divide an integer by another integer, the sort of cases? Well, it's based on the remainder. So divided by 4, there's 4 different possibilities for n. But if n is a prime, so for a prime p, we have the same thing. Either p equals 4k, p equals 4k plus 1, p equals 4k plus 2, or p equals 4k plus 3. And so the claim is that 2 of these cases just don't work, that there's no way a prime could be written that way. And why is that? Well, if p equals 4k, p is prime, but here I have it written as 4 times some other integer. Hence 4 divides it. So this means 4 divides the prime, and the prime itself can't be 4, and so this case can't happen. That implies that p is not prime. That's a contradiction. So do away with that case. Where else do I have an issue? Well, what if p is 4k plus 2? Well, that implies that p equals 2 times 2k plus 1, which means that 2 divides p. Wait a second. 7.4, number 20. We got to have another condition on this, don't we? So 7.3, number 20. Yeah, let p be greater than or equal to 3. I missed that assumption because it's possible this could be 2. Could be even. That would be the only one that would work. But here we're assuming p is greater than or equal to 3, and so this means 2 divides p, but p isn't, p is greater than or equal to 3, and it's a prime, and so this can't happen either. And so that means that this one and this one are the only two possibilities. So if you have a prime, it must fit into this case or this case. Can't have this one, can't have that one. That's it. That's the whole thing. All right, let's keep trucking. I got a couple other ones for you now from section 4. So in this one we have an integer a, and we want to prove the statement if a squared is not equivalent to a mod 3, then a is not equivalent to 0 mod 3, and a is not equivalent to 1 mod 3. That should be a not equivalent to with a parenthesis. Geez, what was I doing? Okay. I have a lot of not equivalent to's. If I do a contrapositive of this thing, I should just have equivalent to's. And that's going to be nicer to work with. When everything is negative like this, I want to make it positive. So I'm going to prove this by contradiction. So what would be my assumption then? What am I trying to do by contrapositive? So careful here. So here's the hypothesis of my implication. Not that would just be a squared is equivalent to a mod 3. So that'll become the conclusion. That's great. We know what the conclusion should be. A squared is equivalent to a mod 3. So I'm going to say, but what about over here? So the conclusion of this is a conjunction. A is equivalent, A is not equivalent to 0 mod 3, and A is not equivalent to 1 mod 3. So think of this like P, and this is Q. Then this statement would be P and Q, and I want the negation of that because I'm doing a contrapositive, right? So this is not P and Q, which is the same thing, which is an equivalent statement as not P or not Q. And so the hypothesis of my implication in the contrapositive would be A is equivalent to 0 mod 3, or A is equivalent to 1 mod 3. So if I'm going by contrapositive, my assumption, well, I have two cases. So assume A is equivalent to 0 mod 3, or A is equivalent to 1 mod 3. So this gives me my two. Anytime I'm split up into two possibilities like this, I can use a cases argument. So case 1, I'm just gonna write this in green. This is gonna be case 1. And this is going to be case 2. So assume A is equivalent to 0 mod 3. So case 1. So if A is equivalent to 0 mod 3, what does that mean? That means that I can write A equals 3k. Oops. My brain got ahead of my hand. A equals 3k for some k. Okay, and what do I want to conclude? I want to conclude that a squared is equivalent to a mod 3. Well, let's compute a squared. A squared would be 9k squared. And you know what? I'm actually going to, if a squared is equivalent to a mod 3, I'm going to subtract the a over. This would be the same thing as saying a squared minus a is equivalent to 0, or not equivalent to 0 mod 3. And so in the contrapositive, I'd want to show a squared minus a is equivalent to 0 mod 3. So I'm going to take a squared and subtract a here. A squared minus a equals 9k squared minus 3k. What do you know? I can factor 3 out. 3 times 3k squared minus k. So a squared minus a is equivalent to 0 mod 3, right? Because 3 divides it, and hence a squared is equivalent to a mod 3. Did it. That's this case. All done. Got it. Boop. Case 2, a is equivalent to 1 mod 3. Well, what does that mean? That means I can write a equals 3k plus 1. And this is going to be another one where I'm going to let you finish the argument. Compute a squared. Figure out what that is. Take the difference of a squared and a. And check that that's equivalent to 0 mod 3. Check that it's a multiple of 3. I'll leave you with that one for this. It's not too bad. This one's not too bad when you see, I mean, that it requires some leaps, right? You gotta notice, hey, we should use a contrapositive here. You gotta remember De Morgan's law of negation, right? How to negate a conjunction. But once you have that, then again, it reduces to writing down what things mean. Well, if A is equivalent to 0 mod 3, what does that mean? It means 3 divides A. So that means A equals 3k. If A is equivalent to 1 mod 3, what does that mean? It means A equals 3k plus 1 for some k. It devolves into that, and then it's just some algebra past that point, and remembering what you want to show. So it's definitely a bit of a challenge. I'm not saying this should be easy for you. It should be a bit of a challenge, but what I'm trying to express here is that if you remember the laws of logic, and you are able to recognize when to use a contrapositive, then you can sort of just follow your nose to the answer. But you need those base things. You need the definitions. You need to remember how to apply laws of logic. And you need to be able to recognize when a contrapositive is a good idea. Okay, let's move on. Number 8. So here we want to show if A is equivalent to B mod n and C is equivalent to D mod n, then A plus C equals, or A plus C is equivalent to B plus D modulo n. Well, I don't see a lot of negatives here, so I'm just going to try this directly. So let's do that. So assume A is equivalent to B mod n, and C is equivalent to D mod n. So A equivalent to B mod n. Well, there's a couple things I could do past this. I think how I want to do this. A plus C equals B plus D mod n. So I could go back to the definition of what it means for two integers to be equivalent, modulo n. And that means n divides their difference. So this thing is true if and only if n divides their difference, A plus C minus B plus D. So if I can do that, if I can write A plus C minus B plus D as some multiple of n, I'll be done. Over here, I'm going to have A minus B. Okay, I think I'm going to do it like this. I think this is going to work because A equivalent to B mod n, what does this mean? This means that n divides their difference. So n divides, I don't know, how about it? Yeah, A minus B. And C equivalent to D, well, this means that n divides their difference, so C minus D. Cool. What does that mean? N divides A minus B. That means A minus B equals some multiple of n. So I'm going to say, I don't know, how about n times x? And C minus D, I can't use x again, so I'll say n times y. And notice over here, A plus C minus B, this is the same thing as A minus B plus C minus D. I could write it like that. And why would I want to do that? Well, that's the equations that I have over here. A plus B and C minus D, or A minus B and C minus D. So if I add those two things together, what do I get? So it follows then that A minus B plus C minus D is equal to nx plus ny. And so I can factor n out. X and y are integers, so x plus y is an integer. And so n divides A minus B plus C minus D. Hence, n divides, how did I have this written before? A plus C minus B minus B minus D. No, minus B plus D. That's how I want it. Let me do a quick check, look up here. Yep, that's what I want. And so n divides the difference of A plus C and B plus D. Hence, A plus C is equivalent to B plus D modulo n. Now, there's definitely going to be other ways to do that because we have these corollaries that, like, we know that if A is equivalent to B mod n, then A equals B mod n. Or sorry, that A, yeah, that A mod n is equal to B mod n. So we could have gone there. So taken this and write A mod n equals B mod n, and over here we could say C mod n equals D mod n, and where would we want to end up? We would want to end up with A plus C mod n equals B plus D mod n. I think we could have gotten there that way as well. That's certainly a way to do this. Okay, so that's it. That's all I wanted to show you from this chapter. Let me make sure I didn't miss any. Let me zoom out. Yeah, that's everything I wanted to show you. So there's some homework problems for you. Hopefully this will help you on the exam. I'll get this uploaded as soon as I can. All right, thanks for listening. See you later.